Good morning. Welcome back. We are in the part 2 of our series. In this, we will see multi-stage decision making problem. In the last class, we have seen how a machine can learn by just seeing the rewards. How a machine can learn to make a single stage decision. Like you have to make from a set of decisions, you have to take one decision. How can a machine do it? In the enum-bundled problem, we had to choose from, say, 10 actions, what are the best action? And there was only one action to be chosen from the 10 actions. So we saw that that could be achieved. It has another name before reinforcement learning came. It's called learning automata. Now in this lecture, I will talk about multi-stage decision making problem. And throughout the series, we will be sticking on to multi-stage decision making problem. Reinforcement learning could be used to solve various stochastic optimization problems. One way to handle is to formulate it as a multi-stage decision making problem, or more formally as a Markov decision process. To this end, I will explain a simple grid world problem, so which you can relate, which you can simulate, which you can play around and understand the basics of Q-learning. Then the objective of this course is there are a lot of decision making problem out there in various engineering domains. Say, let it be electrical engineering, power systems. As I mentioned in the initial video, the power system scheduling is a major area where RL could be applied, because you have to make a sequence of decisions there. And another area is in robotics, where a robot has to take a sequence of decision to achieve some goal. And there are applications, say extension of robotics is UAV or drones. There are, in all fields, there are many fields where reinforcement learning could be applied. To the best of my understanding, RL will be a candidate tool if you have to make a sequence of decision under uncertainty. Then RL is a very, very promising tool. So let us look at what is a multi-stage decision making problem. A multi-stage decision making problem involves making series of interconnected decisions over time to achieve a desired outcome. What is an example for that? Suppose you have a robot. A simple example will be, suppose you have a robot here, and the robot has to reach some goal state. When robot takes a decision, it has to decide by how much, what velocity it should move, in what orientation it should move. It can move like this, then it can move here, move here, move here, move here, move here. Maybe there is some obstacle here. I'll put a color. This is an obstacle. When it sees the obstacle, it has to take a detour. When it sees an obstacle, it has to take a detour. Take action. So there are many actions are to be taken, and finally it reaches goal. So this is one thing which you could perceive, and there are a lot of work which has incorporated this in real practice, where you have a real robot moving from one point to another. There may be a lot of obstacles. Here, to make things simple, I made obstacle static. There may be some moving obstacles. There may be some randomness in the obstacles appearing. So this is one example of multi-stage decision making problem. So here the characteristics of multi-stage decision making problem is it involves a sequence of decisions. It is sequential in nature. It is they are the actions we call decisions in RL paradigm. It's called as actions. These actions are interconnected and they are sequential in nature. One action comes after the other. Then whenever there is an action, there is some concept called state, which will be clear by the end of today's lecture. There's a concept of state, and you take an action, the state will change. For example, the state could be anything. In the case of robot, the state could be the position of the robot, its x and y coordinates, plus its orientation. You may have a robot, let me draw a better figure. This is a robot, the orientation here is forward, and when I say move forward, the robot will go in this direction. But if the orientation is in this direction, when I say move forward, it will go in this direction. So it should know the orientation of the robot. Robot may have lidar sensors or proximity sensors, so you'll get the values of that. So when you take a decision, you will reach in a new state. So RL can learn by interacting with an actual environment or a simulated environment. You don't require a precise mathematical model. And another characteristics of multi-stage decision making problem is the uncertainty. So another common example which I always say about multi-stage decision making problem is, suppose you are traveling from, say, Koilon in Kerala to Bombay. So there are various routes which you can take, and you can, from Kollam or Koilon, you can go, let me try drawing it. So this is our India, the part of India. Kollam is somewhere here. I can take various routes. I can go from Kollam, I can go to Ernakulam, and then Mangalore, then Goa, etc. I can go to Bombay. Another set of decision is I can go from Kollam, I can go to Trivandrum, and then I can go by a different route. And more interestingly, the options are from Kollam you can go to Kochi, and from Kochi you can take a flight to Mumbai. So the decision, if you are going to Kochi, then you will have to take the flight from Kochi itself. But if you are going to Trivandrum, you have to choose some options if you are going by flight. So there are n number of options, and each of these options, the decisions are interconnected. So these kinds of problems are called multi-stage decision making problems. So let us see a very simple toy example, but concrete, to understand the terminology, so that the idea of this video is a lot of work going on, lot of advances has happened in reinforcement learning. So I don't want this specially dedicated to my MTech artificial intelligence elective students. This video is for them. So for my students, what I want is, when you hear this video, you will understand the terminologies of reinforcement learning. Then you will be in a position to read advanced papers, you will be positioned to read advanced videos where people are using various techniques for reinforcement learning. Various algorithms has come up. Reinforcement learning became so popular by Sutton Barto's book, which is the basic reference for this course. The book was published, the first edition was published sometime in 1998. It was followed, its a running edition is there, live edition is there, 2018, The edition is there for you, freely available in the net. So after Q-learning, one of the major boost for the applications of RL was the development of the algorithm Q-learning. So after Q-learning, many other algorithms have come. One of the prominent algorithms is called DQN. I'll put it in the last slide then. So many things have happened. So the objective of this video is for you to read other papers. So I'll tell more about it in the last slide. So let us consider a toy example. Consider this example. This is called a grid world, where I have marked cells as 1, 2, 3, 4, etc. 6 and up to 36. What is the problem here? Find optimal sequence of actions such that the total expected cost from start state to goal state is minimized. So this is a very simple problem. The thing is that if this entire picture is available, there is nothing for you to learn. It's very straightforward. But the point is, the agent will not be having this global map of the grid world. What agent will know is, it will know when it takes an action, it will go to the next state, and it will know if the next state is a block, it will know it's a block. If next state is a wall, it will know it's a wall. That's all. By interacting with such a simulation model, how can I find the optimal sequence of actions such that the total expected cost from start state to goal state is minimized? So putting it in a mathematical framework, the objective of the problem is to find optimal sequence of actions A0, A1, etc. An minus 1 such that the total expected cost is minimized. What is the total expected cost? Expectation of sigma gamma raised to k g xk ak xk plus 1. What is this gamma raised to k? So let us let me explain this term within the curly bracket, within the braces. Sigma k is equal to 0 to n minus 1, gamma raised to k g could be written as gamma raised to 0 g plus gamma square g x1 a1 x2 plus gamma raised to 2 g x3 a3 x4 like that up to n minus 1. So this g is the one step cost or one step reinforcement. So when you are in state xk, you take action ak, you go to state xk plus 1. Then in this framework, in the RL framework or in the Markov decision process, it will give a reward given by this expression. So the objective is to minimize this expectation. Why expectation? Because we are interested in general finding sequence of actions such that the expected cost is minimized. Why expectation? Because if the rewards are random, if the environment is random, every time you may get different rewards. So you want to have a sequence of actions such that the performance is good on an average. Gamma is the discount factor. What is gamma? Is the discount factor. What is it? I'll give you with a very simple and clear example. Gamma, if you want to, you are as a human being, we are making a lot of decisions, and our goal is not instant gratification. Our goal is long term. We want to maximize our happiness. So it's very clear that smoking is injurious to health. But when you smoke, smokers may get some pleasure. You want to maximize your pleasure. But what is the problem? If you smoke down the line, say maybe after 10 years, 11 years, you may get some lung disease, you may get cancer. But even then people smoke. So those people who are smoking, they smoke because unknowingly they put gamma a very small value. So 20 years down the line, if something is going to happen, gamma raised to 20 will be a very small number if gamma is say 0.8. So what is the value of gamma is up to people to people. So if you don't take gamma also, there is another issue. In this case, in the smoking case, it's better not to take gamma. But think that if you do something, there will be some catastrophic or some minor problem will be there later on. So then there will be a decision paralysis. Okay, so I don't want to be philosophical. So gamma is the discount factor, which says that the future rewards, if the future reward is as important as the current reward, gamma will be 1. So the effect of gamma will not come into play. If the future rewards is slightly important, then gamma may be taken as 0.99. If the future rewards are not at all important, you are short-sighted, you want instant gratification, then gamma could be taken as 0. So then you will try to minimize the immediate cost or maximize the immediate reward. So the objective of this video is to make you familiar with all these terminologies. So what are the challenges here? The cost incurred could be random. There could be some block where the cost is random. It's not a very permanent block. The block is kind of sometimes it's a bad road, sometimes it's a good road, or sometimes, so that kinds of things can happen. The transition function is stochastic. Here in the simple example which I will be considering, I will assume the transition function is deterministic. That is, if you are in cell 10, if I say move right, it will move right. If you are in cell 10, if I say move up, it will move up. If you are in cell 10, move down, it will move down. But it could be, if you are in cell 10, if you say move right, it may move right with a probability 0.9 and it will remain there with some small probability. Such cases could be there. So in this simple problem, we have an agent which could move around this grid world. There are 4 actions, right, left, up and down. So the number of probabilities, number of possible routes is 4 raised to 35. And another challenge is you don't have this big picture, you only have a simulation model. So in such cases, reinforcement learning is a good tool. So when you are designing RL algorithm, so let us take a small break. We will continue after a break. Thank you.